Alright guys, welcome to lecture 3, velocity and speed. Okay, here are your learning intentions and success criteria. I do apologize, it's in colour today. Not in colour today. Please complete the KS table. Pause the video while you complete this. Alright, so having a look through here, having a look at the success criteria and our learning intention here, we're talking about definitions of velocity and speed, and we're seeing this calculate verb pop up again there. So through our success criteria, we've got defines a knowledge-based criteria, so hopefully you recognise that we need to, well, firstly know what is velocity in the first place, and through that we'll know what speed is. And this one here, compare. Now compare is about knowledge, because we need to have two bodies of knowledge in this case to compare something. And so we want to compare what is instantaneous versus average speed. And then finally we've got that calculate verb popping up again, and we know that calculation is a doing. So can we do that? Can we calculate velocity and speed? Okay. Now, in the last video, I spoke about distance being the length of the path you travel, while displacement is how far you are from the start. I want to do a bit of a recap on that because it's going to be important for this. So let's say distance is how far you go, versus displacement, which is how far away you end up. Okay, and as I said, that's a really horrible W, I'll just fix that up. As I said, you've really got to understand the difference between those two things. How far you go, how far away you end up. So, when we examine distance, all we do is we add up the individual pieces of whatever story we're hearing here, and that's our final scalar amount. In contrast, displacement looks at the differences between where we start and where we finish. Often we give the start coordinate a 0, but not always. Now, we're just going to be dealing with one-dimensional systems, things moving on a straight line. And a lot of the time that means distance and displacement will be the same. So let's do a quick example of this. Let's say you're walking from home, let's draw a little wonky house, to the bus stop. Draw a sign for the bus stop. So you're going to walk that far. Now, the distance from your home is 200 meters to the bus stop. Now, if you were to walk from here to here, what distance have you covered? Well, the distance would be equal to 200, because you've just gone straight there. But the displacement, well, if we say that this is 0 and this is the coordinate 200 because it's 200 meters away, we can see that the displacement equals, well, final takeaway initial, 200 takeaway 0 equals 200 meters, let's say east, because we'll take it to the right as being east. That's a fairly common convention. Now, this working out here of doing 200 minus 0 is not necessary, but I did this on purpose because, let's say instead of having this as 0, I had this as negative 100, and then this as positive 100. Well, the difference would still be 200 meters east. Okay, and so we find that displacement is always the same. Doesn't matter what coordinate system we use, you'll still get the same answer. Just sometimes we pick things that are a bit easier. Making that 0 meant we didn't really have to do any fancy math. That's why we can choose. But let's take a story where the movement might have multiple steps, because then the distance will be different. So let's say, for example, you're walking from home to the bus stop, but you only make it about 20 meters up the street before having to turn around and go back. So we'll say that is at point 20 meters. You forgot your phone. Okay, so you're 20 meters up the street, tapped your pocket, realized, shit, I forgot my phone, I've got to go back. You head back, you get your phone, and then you walk to the bus stop. And then from here, now I've drawn this sort of wiggly thing just to show the different steps. That's not implying that you're moving in 2 dimensions, we don't care about that. It's just to help us visualize it. So on this new situation, let's call this D1 and S1 because it was our first one, what's our new distance going to be? Well, let's look at the pieces. We walked 20 metres away, then we went back, so we had to go another 20 metres back. And then we went 200 metres to give us a total of 240 metres of distance. But what's our displacement? Well, we ended up 200 metres away, and we started 0 metres away, so our displacement is still 200 metres east. Okay. Displacement only cares about change in position. What you did in the meantime to get there doesn't matter. Where did you start? Where did you end up? Where did you start? Where did you end up? Distance is a scalar. It wants to know every little step that you did. Okay? Displacement just cares about where did you end up? Where did you start? Figure out the difference. Okay, so keep that in mind. Okay, you've got to keep that in mind. Okay, so in our next bit, now we're going to look at velocity and speed. So we've really heavily emphasized this distance and displacement bit. But in physics, knowing how fast something changes is very useful. Okay, and so we have two definitions here for velocity and speed, and I would recommend you check the glossary at the back of the textbook as well in order to look at their definitions for velocity and speed. So velocity is the rate of change per time of displacement. That's all that it is. Okay, we are defining it as saying, well, how fast does this thing change? How fast did the displacement happen? That gives us now time. Is normally in seconds. That's our SI unit, that's our standard unit in seconds. We can certainly still see it in hours or minutes, but for calculations, try to put it back into seconds because it will help you down the track. Doing it in hours is sometimes only acceptable just because there's an easier conversion. Now the symbol for velocity is V. Because we are talking about the change of displacement, and displacement is a vector. Sorry, on my previous slide I really should have been drawing S with a little hat on it. I do forget them a lot. Velocity is also a vector because it's just a vector divided by time, which is a scalar. So V needs our little hat or bold or arrow, whichever it is you prefer to do. As I said, I would often forget when I'm not really paying attention to it. And the standard unit for velocity is meters per second, because that's what the formula is going to do. Now, there is one really important thing to remember, is that while meters per second is the standard unit, often these will be given in kilometers per hour. So this is something you will probably want to write down. Kilometers per hour. To turn meters per second into kilometers per hour, we multiply by 3.6. To convert backwards, we divide by 3.6. And one thing I always remember, just to help me keep in mind, is that meters per second is always smaller than kilometers per hour. So if I have 100 kilometers per hour, my meters per second is going to be a smaller number. Okay, it's about 27 or so. But that's how I double check in that. Do I need to divide by 3.6 or do I need to multiply by 3.6? This is always smaller than this in terms of its size of number. Okay? And then I need to remember the conversion factor 3.6. This will never appear on a formula sheet. I will show you in class how to do it without a formula, so the actual process behind it, but I just memorize this factor nowadays. Okay. If we go into our next area, so speed, well, what's the difference? Speed is just the rate of change per time of distance. Again, time is still in seconds. Okay. Speed doesn't really have a standard symbol. Some of the textbooks will use v with a subscript average. I don't really like that because it's trying to say that speed is directly linked to velocity, and it's not. So I will use the symbol sp because we don't really calculate it all that much. It is scalar, so it just cares about the size. It's just a magnitude. For example, a lot of you be at this point getting ready to learn how to drive. The speedometer on the car is a measure of, is a scalar quantity. It's just telling you how fast you're going at that point, and it's not actually giving you direction or anything. So it's a scalar value. The units are still meters per second. Okay. And so from these formulas, from these definitions, we get our first formula for calculating in physics. Okay, so our formula for velocity, v, is equal to displacement divided by time. Sometimes you'll see that they will put change of displacement at the front because they're after, they're trying to emphasize that whole, well, start versus finished, but if you just write s divided by t, that's perfectly fine. And in your workings out, on exams, for example, if you wrote v equals s over t and you didn't include hats or arrows or bolding or anything like that, you wouldn't get penalised for it. In your student experiment and your research question later on this year, that would penalise you if you didn't use proper writing convention. So just remember it for your assignments. The formula for speed, speed equals distance divided by time. Okay, so the rate of change per unit time, or rate of change of distance per time, we've got our d, we're divided by t. Rate of change of displacement, we've got our displacement s, which is divided by t. So using these formula, let's look back at our previous question about our trip to the bus and work out our velocity and time. So let's put this in here somewhere. So here are our values. So this one here, where we had our first one, we've got our distance and displacement equaling 200, and here's our second one where our distance and displacement. As I said, this should probably have a hat on it because it is a vector. Alright, so let's do scenario 1. So for scenario 1, velocity is equal to displacement divided by time. I know from the question that, or I know from this story here, that displacement is equal to 200. And in this case, let's make up a time. Let's say that it takes 5 minutes. Equals 5 minutes. Now 5 minutes, we need to convert that to seconds because our unit that we're using for time is seconds. So 5 minutes, every 1 minute there is 60 seconds, so 5 times 60 is equal to 300. And so now if we put these two values into our formula, equals 200 divided by 300 equals 0.67 meters per second. Now this is an example of good working out. So if you're asking to use a calculate verb, you need to show working out. Stating your variables, writing the formula, showing the working out. That's the important thing to do. Let's have a look at this one here now for speed. So for situation 1, we have our displacement, sorry, our distance is equal to 200. Our time is still 5 minutes, so let's just jump straight to 300 seconds. And our formula is speed equals distance over time. Substitute in speed equals distance 200 divided by 300 equals, again, 0.67 meters per second. Now, I forgot to include one thing up here because this is, I said that this was 200 east. So this has to be 0.67 meters per second east. Well, this is just a magnitude of 0.67. And so we see something really important here. When distance and displacement are the same on a single straight line because you're just moving always in one direction on a straight line, velocity and speed will also be the same. Let's do scenario 2. Scenario 2, we can see that the displacement here is equal to 200. And the time is, oops, time isn't a vector. The time is equal to 300 still. which means then our final velocity should also be equal to 0.67 meters per second east. I'm not going to do the calculation and working out for that one because we can see that the scenario is exactly the same as this. Well, let's have a look at this one. Our distance now is equal to 240. Okay, we're dealing with scenario 2 here where we travelled forwards, then backwards, and then backwards again. Our time is equal to 300. And so now we get our speed equaling 240 over 300. 240 over 300 is the same as 24 over 30, which is the same as 8 over 10 or 4/5, which is 0.8 meters per second. If you want to check that, you can certainly check that. But I'm pretty sure I'm right. So what we see here is that we made our distance longer, but we had to do that distance in the same time, which means our speed had to be faster than our velocity. Okay? So velocity can quite often be less than speed, because velocity just cares about start to end, while speed is looking at what is happening during that bit. Okay? So you will have some practice questions on that in your understanding thing, so make sure to be using that. Now, there's a couple of terminologies we use with velocity, and velocity in this case can be thought of in two different ways. First is instantaneous, and the second is average. Now, if you drive a straight line from point A to point B, and let's say that it is displacement equals 5 kilometers, and the time is equal to 1/12 of an hour, well, the velocity will equal displacement divided by time equals 5 divided by 1 over 12 equals 60 kilometers per hour. Now, that's saying that the average for the whole time was equal to this. But maybe in this section, the speed limit was 80. Maybe in this section, the speed limit was 40. We don't know from this information. All we know is that s equals 5, and it took us 1/12 of an hour to do it, 5 minutes to do it. Right? So there could have been bits where I was going faster, there could have been bits where I was going slower, but the average for the whole time is equal to 60 kilometers an hour. So average velocity is this formula here that we've been learning about. Average velocity is just telling us what is going on here. Now, so let's write underneath this, V equals S over T. There's no formula to calculate instantaneous. This is something that needs to be told to you or measured when you're doing experiments. One really good example of seeing instantaneous speed, though, and speed can be used, these same words as well, is a speedometer, like I said before. The speedometer tells you your speed at that exact moment in time. Now, if you drive from point A to point B, from, say, maybe you go from home over to Mount Omni Shopping Centre, and you know that it's a distance of 10 kilometres and it took you 8 minutes to do it, you could certainly work out your average speed. But does that mean that you went that same speed the whole time? No, of course not. You started off still motionless. You drove through the streets at hopefully a safe 40 kilometres an hour. You would have got on the highway maybe and gone at 100 kilometres an hour along there, and then you would have stopped at some traffic lights for a bit, maybe gone around a corner at a slower speed for a few metres. Your speed is constantly changing. But you know the instantaneous speed by looking at your speedometer, and then we can work out our average from the whole trip. Now, we will see some examples of instantaneous in experiments. Okay, so I will say this, that instantaneous generally has to be measured, Okay? There are some ways of calculating instantaneous velocity if you're talking about accelerating systems, and we'll see that when we look at our equations of motion down the track, while average is normally going to be the whole trip. Well, that's what average means. It actually does mean the whole trip. So it's important to note these words. For example, if we're talking about a race car driver traveling across a track and they cross the street, they cross the finish line at 200 kilometers per hour. That doesn't mean their average was 200 kilometers an hour, because they may have only covered the average at so the whole thing at 50 kilometers per hour if we look at the displacement divided by the time. So that's an important thing to realize, that average normally is calculated while instantaneous is normally measured. Okay? And we'll use speed to look at these as well, because speed and velocity on a straight line are the same thing, as we just saw with our previous bus example. Okay, now I want you to take a look at the worked example on 10.3 on page 283 of your textbook, and I want you to note the use of distance to calculate average speed and displacement for calculating average velocity. Also note that Walding has used kilometers per hour as the final units. On your Year 12 exam, I would be very, very careful with things like that. While kilometers per hour is reasonable from our perspective, we can understand it pretty easily. If I tell you, oh yeah, it's going 60 kilometers an hour, you can go, oh yeah, that's how fast my car goes, I know that. Or if I tell you that it ends up going 10 kilometers per hour, you can go, oh, that's how slow I've got to go when I'm driving the car through a shopping centre car park. So we've got a perspective of this. The standard unit is meters per second. On your final exam, or on your data test exam, unless I ask you otherwise, you must always give me an answer for velocity in meters per second. Right? And quite often the exams will tell you what units to give the answer in as well. But the standard is meters per second. Only do something different if it's been asked of you. Okay, so just keep that in mind. Alright, learning summary. So in this video we have learnt the following. We have developed our definitions of velocity and speed. We've discussed instantaneous and average velocity and speed, and we've identified the formulas to calculate velocity and speed. Okay. For your entrance slip to class, you've got a little bit more work to do. I need you to complete questions 1 to 5 in the chapter 10.3 Check Your Learning PDF. Remember, you can download it from your O-book, or you can just access the textbook itself. Copy your answers for questions 1 to 5 into the 1.3 space on eLearn. Now we will be doing a lab next lesson on this content. I need you to read over mandatory Prac 10.2 on page 485 at the back of your book before class, so you are familiar with what we will be doing. Okay, so you've got both answering the questions into the web space and reading over the prac, because I want you to understand the method before we go in, and there will be an Excel sheet provided for you, so make sure you've got your laptop with you. Thanks very much, guys. Catch you in the next video.